Check point 2. An ideal gas has temperature T1 at the initial state I as shown in PV diagram here. The gas has the higher temperature T2 at final states both A and B, which it can reach along the path as shown in the figure. Is the entropy change along the path to state A larger than, smaller than, or same as that the path to state B? So in this question, we have to use the PV diagram. So what is given in the PV diagram? We have the initial state and then we have two final state. So initial state, the initial temperature is T1, and final states you have 2 points A and B. So your temperature increases to this level. Now they ask you to find whether the entropy for path A is greater or path B is greater. So that is our question. So for that, we can see the PV diagram. If you see the PV diagram, let's we consider process B. That means I to B I am going to consider. So in process B, you can see the process is exactly tells about isobaric. So let's we consider this part. I am going to consider the point from I to B. That means at I point the temperature is T1, at B point the temperature is T2. And if you consider this, if you see this PV diagram, this line I to B exactly tells about isobaric. So I am going to write for process B here. In process B, based on the PV diagram, it is isobaric. What is meant by isobaric? Pressure is constant. Pressure is constant. Clear? For pressure is constant, let's we find the entropy. What is the formula for entropy? The formula for the entropy here is dq over T. Right? So, and also I'm going to use this formula for these two lines. So let's we consider process B. In process B, the reaction is isobaric. That means the pressure is constant. So I'm going to apply in this entropy formula. If the pressure is constant, what is the heat supplied? Which is dq, which is equal to N Cp delta T. So what I'm going to do, I'm going to take this value, I'm going to substitute here. So if you substitute, you will get entropy of 1 for process B, which is equal to integration the initial temperature to final temperature dq over T. After we simplify, we got this rule as Ti. So first of all, let's I substitute the value for dq. In place of dq, I have to substitute N Cp delta T over T, and after that I'm going to take the constant term outside. So therefore S1 of B, which is equal to N Cp, we can take it outside, and when you integrate, this is not because when you integrate this dt, so dt over T is natural log of T. So the initial temperature is the lower limit, final temperature is the upper limit. So after you simplify, we got N Cp Ln of T final over T initial. So that means this is S1 for B. So let's we consider this is our first situation. Likewise, we have to now consider process A. That means the vertical line. So in vertical line, this clearly tells about constant volume. When there is a constant volume, there will be no work done, right? So let's we apply the rule for process B. So process A. So process A, the reaction is here is isochoric. What is by isochoric? It refers to volume is constant. Clear? Now, for volume is constant, dq formula is NCV dt, right? So I have to substitute this in entropy formula, which is dq over T. So when you substitute this formula here, like what we did in the previous part for isobaric, you will get for S2 for process A, for process A or B. I think for process A. That means the previous one is for process B. That's right. So S2 of A, which is equal to integral of NCV dt over T, initial temperature and final temperature, and then we can take NCV outside. So integral of dt over T, T initial and T final, which gives the value of natural log of T, which is equal to NCV natural log of T, initial temperature and final temperature. After we substitute NCV ln of Tf over Ti, this is for process A. Clear? So let's we take this equation as 2. So now what I'm going to do, I'm going to compare equation 1 and equation 2. So let's we divide 1 by 2. I'm going to divide 1 by 2. So divide equation 1 by equation 2. First of all, let's we start with the left hand side. S1 of B, S1 of B over S2 of A, which is equal to NCP ln of T final over T initial over NCV ln of T final over T initial. This term get cancelled, N get cancelled, right? So what is remaining? Entropy first value of B process over entropy second of A process, which is equal to Cp over Cv. So generally, the Cp will have the greatest value than Cv, because at constant volume, there is no work done. So the constant volume only helps in increase in the internal energy change. But your constant pressure, that means Cp value, not only it will focus on the internal energy, it will deals about change in volume also. So generally we know that from the theory class, we know that Cp is always greater than Cv. So based on this concept, the entropy during the process, that means the entropy process for B is greater than the process A. So B process is greater than A process. So this is the answer for this question. That's it. Thank you.